www.nanohub.org. You can follow along with this presentation using printed slides from the NanoHUB. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
So we had a question that said, when we talk about high mobility channel materials like 3,5s or graphene replacing silicon, how would it exactly be better? Is it that we can make transistors with the same current levels at longer gate lengths? As using longer gate lengths, it's easier to manufacture and control the channel length. All right, so it's a good question. I can't say a lot about that, and let me. When you make a transistor people would like to have a lot of current when the device is on. So at a given voltage, as low as possible, a volt. If you could do a half a volt, it would be even better. You'd like to get a lot of current so that you can charge and discharge all of the capacitances, do the wiring and everything on the chip and run very fast. And you would also like the channel resistance down here to be as small as possible so that the current goes up very rapidly and saturates, and it doesn't take a large drain voltage in order to saturate, because power goes as voltage squared, so you could operate at lower voltages. So you'd like this curve to be steep and you'd like this value to be high. So down here, traditionally we write the current as W mu. They call it effective mobility. Well, we'll just say mu here. Figure out what mu it is. Gate capacitance, Vg minus Vt times Vds. All right. So this is a lot of the reason that people were really interested in 3,5 transistors or graphene, because the mobilities are very, very high. They looked at this. Maybe this is 200 centimeters squared per volt second for silicon. Maybe you could get 10,000 on some of these 3,5s. All right, that looks like an enormous boost. All right, but it wouldn't quite work that way. I mean, that would give you more steepness, but you're going to saturate. And also, you can't get steeper than the ballistic limit. So this mobility really here, 1 over that mobility is 1 over the actual mobility, which might be enormous for these materials, plus 1 over this ballistic mobility. And that's the thing that depends on channel length. So that ballistic mobility, mobility is thermal velocity times mean free path, but in the ballistic limit, the mean free path is the channel length, right? Divided by 2, that's diffusion coefficient, and then the Einstein relation divided by KT over Q. So as you scale and get transistors denser and denser and denser, this ballistic mobility gets smaller and smaller and smaller, and it tends to dominate. So you get some boost, but you don't get nearly the boost that you would expect just by looking at the differences in the bulk mobilities. Okay. But there is this advantage, alluded to in the second question. Is it that we can get the same current levels at longer channel lengths? Yes. So with relaxed geometry, especially if you're looking at RF devices, you can get very high performance. Oops, this should be W over L. I can go to much higher channel lengths where the ballistic mobility is bigger, so it doesn't limit things as much. Now we're limited more by the actual mobility, and that's so much higher in 3,5s or graphene that in a longer channel length device you could still get very good RF performance or high-speed performance. So if you're looking for RF performance, that's an advantage. If you're looking for density in a digital circuit, you're going to make these transistors as small as you possibly can. And then this ballistic mobility is going to limit you. Now, also up here, I mean, you tend to get more, more current. You know, you can see that this mobility has a thermal velocity. So 3-5 devices, it's a little bit harder to think about it in graphene, but you have to think about what the effective mass is in graphene. But similar things happen. If I have frequently I have a high mobility because I have a very light effective mass. That light effective mass is also going to give me a very high thermal velocity. That thermal velocity, remember what the on current was. It was W times Cox times the ballistic injection velocity times Vg minus Vt. So what's giving me the high mobility, part of it is due to low scattering, part of it is due to light effective mass. The light effective mass is also giving me a high injection velocity. So that's boosting my on current. That's good. I'll have a higher ballistic limit in those materials. Okay. But there's always a gotcha somewhere, right? You know, it's always a trade-off. So there's one more issue that we can't, I probably can't do justice to, but I will point out. In an MOS transistor, so let's say I have a source, I have a drain, and we have a gate insulator, and we have a metal. Right? When I've been talking about the gate capacitance, I've just written the oxide or insulator capacitance. All right. And that's epsilon of the oxide divided by the thickness of the oxide, which is like a little over 1 nanometer these days. So this is the capacitance in farads per square centimeter. Okay. But that's not quite true, because the semiconductor channel itself also has some capacitance. So the actual capacitance is this insulator, or insulator, if you've replaced SiO2 with something else, like Intel has, then it's some other insulator capacitance with a different dielectric constant. But it also has in series with it a semiconductor. Sometimes people call this the quantum capacitance. These two are in series. So here's my gate terminal. Here's the surface of the semiconductor, or the middle of the channel. And the actual gate capacitance is the series combination of two capacitors. The physical capacitor formed by this insulator, parallel plate capacitor, and the capacitance due to the semiconductor. And this probably won't come up in your lectures later on, but you can show that this semiconductor capacitance under simple conditions is Q squared times the density of states at the Fermi level. Okay. The 2D density of states is effective mass over pi times h bar squared. Right? So in 3/5, the light effective mass that's giving you the high mobility, that might not be so important because your ballistic mobility is going to limit you, but it's also giving you the high thermal velocity, which is important because it gives you a higher drive current, which you want, is also giving you a lower density of states capacitance here. So if I put these two capacitors in series, it's going to lower the overall gate capacitance. So there's a trade-off. The boost that you get from the light effective mass is offset to some degree by the drop in the gate capacitance. Your charge is going faster, but you have less charge. Now, so the net effect is that you get a benefit. But again, you don't get quite as much benefit as you might have initially anticipated. Right? So people are looking very closely at this. It looks like there might be a win there. It's not quite the slam dunk that you might think of if you had only looked at mobility and you had only looked at ballistic injection velocity. But it looks like if you're careful, there could be a place there where you could design a device and get some improved performance. Okay. Anything else I can add to that?
In the ballistic mobility, the thermal velocity weighting, so what's the effective mass to use? Is the effective mass in the metal or effective mass in the channel? Because it's the injected electron from the source, right?
Yeah. So, yeah. Make sure Cyprio agrees with this. You know, what we're doing is electrons are coming in from the source, and we have this top of the barrier. We're populating these states with a Fermi level according to the band structure at the top of the barrier, which we're thinking of as our beginning of the channel. So it's the effective mass at the top of the barrier here, right? We're assuming we know the density of states at the beginning of the channel. Is that right? Yeah. You know, then there are questions. If you get into really small devices, you know, is the effective mass in this very short channel device in that region the same as it is in the bulk silicon? You know, to first order, it's pretty good to remarkably small devices. These days, you know, one of the other reasons that 3.5s aren't quite as attractive an alternative as they were initially is that silicon never stays still, right? These guys are always doing clever things. There's been a lot that's been done in recent years on strain engineering, by straining silicon effectively to lighten the effective mass and get a lot of these benefits, which makes it even harder for anything to compete against silicon. But as I said, you work the numbers, it looks like there's an advantage there, but it's got to be done in a well-designed device.
We talk about the contact resistance of 3.5 and your ballistic. So you talk about the ballistic mobility for 3.5. Mm-hmm. It's better than silicon, right?
Yeah, so the ballistic, for a given channel length, I guess this velocity will be higher, right?
But then we've got to get there's an issue of all the extraneous resistance, so of getting that structure, which is a real resistance.
Yeah, all of this parasitic source drain resistance, so some of these practical issues, which are very, very challenging because you're thinning everything down, you're making all of these parasitic resistances higher, you know. These resistances are probably scaling in the wrong direction. They want to go up with scaling because you're shrinking all the dimensions, right? You're shrinking the cross-sectional area of this resistor. Here you're shrinking the channel length, and this is going down.
What's the VT difference, the potential velocity difference?
Pardon me?
What would the velocity difference be between silicon and potentially?
Oh, this velocity here? So in silicon, it's, so one of the things I really should have done, this really depends on where the Fermi level is in the band. When you're a non-degenerate semiconductor, it's independent of the gate bias, and it's 1.2 times 10 to the 7th centimeters per second. When you start pushing the Fermi level up in the band, that velocity gets higher. So under typical on-current conditions, I think this is more like, 1.4, 1.5, something like that. If you go to a 3.5, that number, as I recall, depending on the effective mass and how light it is, that can be more like between 2 to 3 times 10 to the 7th centimeters per second. Yeah. So there's a possibility of, almost a factor of 2 there. Yeah. Yeah. Okay. All right, if there are no more questions, then I'll turn the microphone over to Professor Dada.
Thinking where to start, there's a number of different issues that people have raised. So maybe one thing we could do first is take a simple example and see how these coefficients, how these things like density of states, density of modes, etc., what they look like. So supposing I have a two-dimensional conductor, width W, length L, and we'd like to get the density of states, number of modes, etc. And usually you assume some kind of a energy momentum relationship here, right? EP relation. So usually you'd say equals E square over 2m. That would be the standard one. So if you want the velocity, then it would look like dE dP, that's the general formula, which would be P over m. That's the standard one. Now the other material of great current interest is graphene, for example, where E looks like some constant times P. So this one, if I were to plot it, it would have looked parabolic. This one, if I plot it, it would look like this. And question is, what is the velocity here? Suppose dE dP. So basically it's just V0. Right? Actually, I don't need this absolute value around because I can think of P as the magnitude and then there's any angle. Of course, then really V equals V0. That's it. Okay. Now, one interesting question is, what is the mass in this case? Because the way I said it is that in order to use Drude formula or things like that, the mass you should really think of as the ratio of P to V. Just as here, of course, that's this mass, no problem. But if you're thinking of graphene, then if you wondering what mass to use, it's really P divided by V. And there you'll notice that you could write P as E over V0, and this V is fixed. So that's like E over V0 square. So the point is, as the energy increases, the mass increases proportional to the energy, essentially. So if you are trying to use a formula like, let's say you're talking of mobility. Mobility, you usually think of it as Q tau over M. And as electrons have higher energy, let's say because you have, when you increase the carrier density, as you know, the Fermi energy is going up, and so the average energy of the electrons is higher up. And usually as you go up, if the mobility goes down, you say that maybe the scattering time is going down, mean free time, but not really. It could be just because the mass is going up. That's it. So most graphene materials, when people actually measure the mobility as a function of carrier density, they find it goes down with energy as you increase the carrier density. And I believe most of it really comes from the mass going up, essentially. That's got nothing to do with the mean free time as such, really, if you're thinking of it this way, right? Okay. So now,
I guess I mentioned that equation there says E is equal to mv squared.
right. So, yeah, when you multiply it this way, it looks like the most famous equation, right? E equals mc square. It looks like that. Yeah.
But people do say that electrons behave like relativistic particles in graphene.
Right.
This is kind of why they say that.
Right. So graphene has, lots of very interesting, and this is why I say that it's important to separate out the simple things from the rocket science. And what happens with this usual way of thinking of transport, I feel, is a lot of simple things look like rocket science, which it shouldn't. That's my point. A lot of this is really pretty, nothing much is involved here. Okay. Now, in terms of density of states, I say usually that the best thing is to first write the total number of states that you have below a certain momentum. And that is kind of the same no matter what EP relation one talks about. And that is the thing I wrote in the morning, that N of P would be like, if it was a two-dimensional conductor, a one-dimensional conductor, you would have written it something like this. And if it's two-dimensional, then you'd actually write it something like this. With a pi. And this is, here the simple argument is that you're just looking at, this is P, X, P, Y, and you're asking how many states do I have whose energy, whose P is less than some maximum value. And so you want to know how close together these states are, and that is where you're bringing in the wave nature of electrons. Everything else, it is all particles. But this is where you're saying, well, the de Broglie wavelength has to fit into the box. That's where the wave nature came in. And that's this de Broglie wavelength fitting into the box type of idea. And that's what then gives you this N. And till this point, there was no quantum mechanics at all in all this discussion. Okay. Now, once you have this N, so let me write it here. Is equal to whatever I wrote there, phi p square. Right. So that's the area of that's the area of that circle, and then each state occupies a region sort of like this H over L, H over W, and that's how you're getting it. Okay. Now, from this N, the way you get a density of states then, that's where the EK relation will come in. Because now you're trying to get a density of states, and that is when you say you'll take dN dE, which is like, you could take dN dP, and then dP dE. Okay. And so the density of states that you finally get would look different here and here. For graphene, it would look a little different from that. Although, as I said, at this level, it was all exactly the same. Nothing was different. Yeah.
In case of graphene, does the velocity depend upon energy and momentum?
So this is the graphene case. So energy is linear with momentum.
And velocity, does it depend upon energy?
Velocity, that's this constant. It's constant, right. So that is why, you see, often one of the things, I said that the masses should be used as P over V. And that is what I can show is what you need if you want to use Drude formula. But usually in textbooks, what you learn is mass is actually, 1 over m is usually dV dP. That is what is usually defined as mass in the textbooks. And from this point of view, in graphene, the mass is actually infinite. Because, and the argument is very simple, that you see, an electron in graphene has the same velocity no matter what you do. So the argument they go with, when you put an electric field, its momentum keeps increasing, because dP dt is the force, and because of that force, supposedly the momentum keeps increasing, but velocity doesn't change, so acceleration essentially is 0. So you say, mass is infinite, that's why it can't. And of course, if you use mass infinite in the mobility formula, you get nonsense. That would basically tell you it shouldn't be conducting, which of course isn't the case at all. Okay? This is why I'm saying a lot of simple things start looking like rocket science. At which point you say, graphene is this very unusual material where you can't understand anything. But all I'm saying is not really. If you look at it the right way, it's actually not that complicated at all. So, right, anyway, so the velocity is constant. So the point I'm making is, although this is what is usually described as mass, in order to use the Drude formula, you should really be defining it this way. So instead of dV dP, you should really be defining it as V over P. Then you could think that way and it would give you sensible answers.
So at E equal to 0, the mass becomes 0.
Right. Because you still have a velocity, but the momentum is 0. Because this is a constant slope. Velocity is the slope of that, which is the same everywhere. So when you are here, it's like you got a lot of velocity without any momentum. So mass is 0.
So what happens to the carrier like that?
What happens to?
The carrier, the electron. Like if the mass is 0, so you apply force. So what's going to happen to the carrier? I mean, it should have a like infinite velocity of it, right?
Yeah, the way you are supposed to use the semi-classical theories is that dP dt is equal to force times electric field. So you're supposed to use the Newton's laws, this in semi-classical theory. When you apply it, the force should be equal to derivative of the momentum, time derivative of the momentum. Right? So the way you should think is, if an electron happens to be here, its P will keep increasing like this. But the velocity will stay the same though. It won't. It's just that, thinking a lot of other things are built in, that we think of this as mv, and then we like to say that the acceleration is qe over m. And what I'm saying is, this is correct in semi-classical dynamics, this isn't. I mean, that should not be the starting point. The starting point should always be this one. Right? When you are applying it to funny EK relations, you should really be starting here, not here. Okay. So, so if you look at this dN dP, that would be proportional to P. You can see. So I guess I could write this. So I won't bother. I guess we could write this out. 2 pi P LW over h square. And then I have times 1 over velocity. So what I've done here is, I wrote dN dP, because this, as I said, comes from fitting waves into a box. Doesn't have anything to do with EK relations. Even if we are talking about phonons and trying to figure out density of states, you could still use that. It's that after that, when you do omega k relations, that's where the rest of it will change. This just comes from fitting wavelengths into a box. And so when you take dN dP, you'll get that. And then dP dE, that's the inverse of the velocity. Now this is where you see, when you try to get density of states, you'll get two different answers for this and that. Because here, what will happen is, the velocity itself is proportional to P. So it will be P over M. And then the P will cancel out. And that's this well-known result for parabolic bands, that the density of states is a constant. Doesn't change with energy at all, because you see that P that cancels out, and then what you're left with is just constants. It will be this m over pi h square type of thing. That's the standard answer. On the other hand, when you do that in graphene, you'll get something a little different, because up to here is fine, but then this velocity is not P over m, it's constant, some number V0, whatever it is. So what that means now is the density of states is proportional to P, and E itself is proportional to P. So basically you'll get a density of states that is proportional to energy. And that's the standard result again in graphene, that when you draw the density of states, it's like proportional to energy. So the picture you usually often draw for density of states is something like this. That would be it. Okay, now the one that, so these are things I'm sure you have seen before. So the part that is probably a different part that we haven't, that you may not have seen as much of is this number of modes. And this is where I guess what we said was that this m over h was equal to this dvz over 2L. Right? And this is what is like dv over 2L. And then there is a numerical factor that comes from averaging over the angle. Because in general, if you think of the velocity, like this is the z direction, and you have a distribution of angles here. So if you want the average value of the z component, you have to kind of take this cosine theta and average over that, which I think gives you a 2 over pi or something, right, that you can check. But this is dv over 2L times. Okay. Now the interesting result is that, yeah, while this is true, and if you take the d and put it all back in here, you'll find that irrespective of the EK relation, finally this number of modes becomes how many wavelengths you can fit in here. You know, just as we wrote this n by saying how many wavelengths you can fit into that box, the corresponding modes is like how many wavelengths you can fit into the width. This is the part that's not obvious, but this is the point I was trying to make. That is because of this general relationship that dvp is n times the number of dimensions, and so dv is like n over p. And so just as n tries to fit wavelengths into this two-dimensional box, m kind of tries to fit wavelengths into this cross-section. This is the part that if you try out a few things, you'll see how it works. Right? So this one we can do it. Oh, so I guess I erased that. So we had this expression for density of states. Times 1 over v, that's d. Okay. And what we are trying to find is what is m. And m is equal to h dv over 2L. And you know, it's supposed to be this vz. So when you average it, I think you get 2 over pi. Not sure if I'm remembering that factor correctly. We can work it out, but for the moment, let me just assume that. So this is d, and what I want is h dv over 2L times that. And note that here I've still not made use of the EK relation at all, which means this should, whatever I've done so far should work just as well for graphene as for anything else. I haven't done anything so far. Okay. So if I take this, I need h dv, so I can take the one h out of here and one v out of here and put it here. So that's h dv. Next, what I can do is I have to divide by 2L. So I'll put a 2L here, and I'll put a 2L here. And then I have this extra 2 over pi. So what I've done is essentially h dv over 2L times 2 over pi, and that basically should be mass. So whatever I have on the left-hand side, not mass, basically should be this number of modes. So whatever I have on that side should be the number of modes. And again, I have not yet made use of EK relations or anything. So it should work in general. So now I think you'll see a number of things will cancel out. 2L, take the pi out. And so basically what you get is 2W over h over p, which is basically as if you're taking this width and fitting de Broglie wavelengths into it. That's it. You see? So this is the point that we're trying to make, that although this definition of M kind of doesn't look like you're fitting wavelengths into anything as it stands, it's like density of states times velocity, which makes a lot of sense. Density of states tells you how many electrons you can put there. To carry current, of course, they need to be moving. They need to have a velocity. So it's not enough to have states. So that's why current depends on modes, and modes depends on density of states times velocity. That makes good sense. But yes.
What is P again?
Momentum. So, right, so momentum equal to h bar k. Right?
So is it the momentum at the bottom of the band and momentum at the front of the level?
At any energy, right? So in this discussion, that's a good point. Let me explain. So whenever we are discussing this, the way I think about it is that we are talking about this elastic resistor where electrons are traveling at different energies. And anytime it is moving at a particular energy, it's elastic. It sticks to the same energy. And so when I think of conductance, number of modes, density of states, anything I write, it is at some energy. Now you say, okay, but then for this conductor, how do I know what exactly to expect? Well, if it is low bias, it will basically involve integral dE minus del F0 del E of whatever quantity we are talking about. So when I calculate number of modes, it is a function of energy. So here, for example, the number of modes we got depended on P, and that I can translate back into energy, because what that would mean is number of modes in a parabolic material would look like square root of E, because M is proportional to P, and parabolic material means E is proportional to P squared. So it would look like square root of E. On the other hand, if you are talking of graphene, then P is proportional to E. So the number of modes, when you translate it into energy, will look like square root of E for parabolic materials, and will look like proportional to E for graphene. In terms of P, it's still the same, because it just fitted how many it is, right? And if you're talking of, say, the ballistic conductance, how much is it? I'd say, well, it's basically Q squared over H times this number of modes. Number of modes at what energy? Well, over all energies, but then you have to integrate dE minus del F0 del E, because all conduction properties tends to be averaged this way, right? For low bias, this usually works very well. Yeah.
So why isn't D at E a very sharp function? So
right.
Some particular energy level where you have that.
Right.
Is that like from level or is it?
Right. So yeah, very good. So before I want to get on to that, but before I move on, I hope this basic math, I guess, is clear. That what I'm trying to say is that usually I always start from this function up to a P, how many you have, and then you can take its derivative, get D, etc. All this stuff, right? And all this then finally will give you a density of states or a density of modes, the basic concepts as I mentioned. Yeah, where this D, F, M, and N. Density of states, Fermi function, M is number of modes, N is number of states up to a certain energy. And conductance usually will depend on that quantity averaged this way. This is one of the points I tried to make, that this del F0 del E looks like, if this axis is energy, looks like something that is peaked right around the chemical potential, wherever that is. So Fermi function, when you look at its derivative, it has a peak there, and the area under the curve is 1. That's the important thing. So in a way, it is taking a weighted average of this. Okay?
So the E you have there is like this. It's around the Fermi chemical potential value.
Yeah. Right. Except that Yeah, let me draw this picture that I had originally. You know, this density of states. And then there's a mu1, mu2, this energy. And this is where I said the Fermi function would probably look like a peak like this. But the same concept, though, would work if we are talking of semiconductors. What I mean by that is, supposing this mu, instead of being here, we are talking of something down here, let's say, you know, with a small bias. So in that case, this df0 dE looks like this. And of course, then all the conduction is happening on the tail of that function. And this is the limit, the non-degenerate limit that Mark talked about. You know, a lot of the calculations in semiconductor texts are usually in this limit. Okay? Because in this limit, you see the Fermi function, as you know, looks like this. And of course, down here, these two things don't look at all similar. But up here, those two functions are essentially just one thing, just a constant times each other. And that's the approximation that Mark was using for non-degenerate conductors, which is that del f0 del E is equal to f0 over kt. That holds up here. That's it. Down here, actually, 1 minus f0 kind of looks like that. But that's a separate string. But otherwise, you know, those two functions are very different. But this one, I feel this function kind of expresses this basic fact. The point I've been trying to make is that conduction depends on things right around that chemical potential for low bias. And for high bias, I'd say what matters is, like say you put mu1 here, you have mu2 here. Then what matters is this entire window. And in this case, though, often I'd say neglecting inelastic processes is not a good idea, because that can change a lot of things in this part, and that I'd like to say a few words about after this. But please go ahead if there's more questions about what we just talked about. Is this point generally clear? Oh, you know, the basic concepts are again that D, F, N, and M. Right? And for a given EK relation, how to calculate them. And as I said, often things like modes as a function of P will look the same no matter what material you are in. You just take width and divide it because you're just fitting wavelengths into this thing. But yeah.
So I guess you're going to be talking about spintronics later. Right. Thinking of spin. We need a factor of 2 in that expression.
Right. That's true. Okay. Yeah. That is one point I should. Just to you know, because these little factors, of course, especially when you're beginning, can really take up a lot of time, and it can really get you very confused. Yeah. What often happens is when people write modes, they don't include spin in it. Because one thing we all know is that, you know, I mean, we all know in the sense you've heard it many times, is that states usually come in pairs. If there's an upspin state, there's a downspin state. And so what you often do at the end is remember to multiply by 2. Okay. Now, the thing is that usually when people talk of density of states, the way I have done this, it's like as if there's no spin. So in other words, I'm talking of density of states per spin. And so, and this number of modes, that's also number of modes per spin. Now, it's just that when people talk about this, they usually talk of the density of states including spin, but then they don't include it in the modes. The modes, they say, well, it's like modes per spin. And so, then instead of a 2, you see a 4 here, because their density of states includes spin, but their modes doesn't. You see?
So that's what they saw in my
Right. And of course, the advantage of that is that it connects with most of the literature, so it will look like what you will see most of the places, right? But in order to keep track of it, I like to keep them. And to me, in a way, spin is a little bit also like valleys, that in some cases you have to include valleys. Right? And all I'm saying is spin, valley, all these things you can bring in later. You know, okay, I've got 2 spins and 2 valleys, and these are all very. So when you look at the ballistic conductance, for example, what is the quantum of conductance? and I said, well, it's q square over h, right? Or if you invert it, h over q square, that's like 25 kilo ohms. Now, if you actually measured the conductance of something, of a small piece in gallium arsenide, what you get is not 25 kilo ohms. So the minimum you get, the resistance you get is actually 12 kilo ohms, more like 12.5. Why? Well, because there's always the two spins in parallel. So that's the quantum of conductance, again, per spin, per mode. But then you always have two spins in parallel. But then when you measure it in carbon nanotubes, you get 6 kilo ohms. Why is that? Well, because there's two spins and there's two valleys that go with it. You see? That's it. So whatever I said here, everything, I tried to write everything in a way as if there is just no spins, no valleys, etc. And then you have to multiply by spins, valleys as needed. And sometimes equations may look a little different because people might include the spins and valleys here but not there and things like that. Right? Because of, again, because of conventions and how they're doing it. Okay. Yeah. Any other questions, please? Really?
Carbon nanotube example again. If you measure the resistance, it's going to be like 6 point something.
Right. So the smallest carbon nanotubes, ballistic, will give 6 kilo ohms. Well, because even the smallest one kind of has these 4 levels, 4 channels in parallel, the 2 spins and the 2 valleys.
You always go back to 25K.
25K is per channel. And then channels can come from spin, from valley, etc. Right, right. Right. Okay, and yeah, were there any other questions related to this? I think, yeah.
What are valleys?
Valleys? Okay. It's like when you look at this energy momentum relation, what happens is, I said that the energy momentum relation looks like this, E versus P. Now, actually, I said that one of the, and this is this part about band structure that you have in crystalline solids, what the E energy momentum relation looks like there, and it is really a fairly complicated function, that goes on, and what you try to do is look at the minimum, because those are the ones that contribute to conduction usually, right? Because, as I said, if your chemical potential is around here, so usually there's a valence band and a conduction band, and you try to look at the minimum here and the maximum here. And what could happen is there could be multiple minimums. So you could have one minimum here and another one here, for example. So you could have something that looks like this. And then you got one here and one here. And whatever we did would kind of apply to that one. So then you'd say, well, I got 2 valleys. And we did all the calculation there, but then this is in parallel with that. So they're all in parallel. So in carbon nanotubes, there's like these 2 valleys that need to be included in this, right? And this is true in silicon, there's the 6 valleys actually. So gallium arsenide is simple that way, one valley keeps it straight. Simple.
That is within single unit cell. That is within single unit cell of any material. We're talking about like 6 valleys inside 1 unit cell of silicon. Like in case of resin, there are 2 valleys inside 1 unit cell of graphene. So here also it's like 6 unit cells inside 1 unit cell of silicon.
So you're saying the number of valleys is related to the number of atoms in a unit cell. Is that what it? That's what I see. Because in in graphene, there are 2 carbon atoms per unit cell. That's true. The reason I'm hesitating is gallium arsenide and silicon, both being zinc blend, probably have the same number of atoms per unit cell, right? But values are different. Because what can happen is this. You could have one material looking like this and another material where this happens to be D value. So in this case, you would say I've got only 1 valley, whereas in this case, you would say you got 2 valleys because those are the lowest ones. Right? So it is hard to predict the lowest one, how many there would be, I think. There's probably no simple connection there. Okay. Any other questions, please, on this? calculated. Okay. Yeah. Now the other question I've had from a number of people, I suppose, is again about the role of electric fields in this current flow, right? And there, let me make a comment that, and this is something I think Mark Lundstrom also touched on, that if we are talking about, let's say, a semiconductor, this is mu1, this is mu2, and you have a density of states like I was drawing, say, somewhere here. And for this discussion, let's assume, this is fixed. So I had a electric field like this. Now, one point I made was that supposing you had this fixed like this, and it goes down, when I calculate the current, it doesn't seem to depend very much on the electric field in here, as you think about it, because all that matters is the fact that these two chemical potentials are different, and the way we are calculating it, you might have, you would obtain a current that would look like Q over H, number of modes, lambda over L plus lambda. I guess this was the expression that we have been working with F1 minus F2. Now, and the one point that Mark made, I think, is that when you put in, that actually, if you're looking at the saturation current, that is when in this energy range of interest, F2 is all 0. So which means you can drop this because there's nothing coming back from this side. You look at saturation current. Actually, the current is a lot bigger than what you might think from this. Because although the length of the device is some length that based on the low field current, you might have thought that it is 50 mean free paths. But when you look at the saturation current, it looks like a whole lot less. Looks like it's only 10 mean free paths. And the question is, why is that part of it? And this is where the way I think about it is that this is something that kind of requires you to go beyond a point channel model and think about what is happening inside the device, the spatial distribution of things. Because if you looked at the density of states inside, it is sort of like you have a density of states here, but then because of the electric field, it is going down here like this. So, because as I said, when you have an electric field, the electrostatic potential is different. And because of the electrostatic potential, as I mentioned, the density of states should be changing this way, dE minus U. So, if the electrostatic potential here is, lower because you have a positive voltage, the entire density of states should be going down. So, what I'm trying to plot here is this axis is energy, this axis is Z, and I'm trying to show where the density of states are. So at this end, it is 0. This is sort of like your band edge. There's 0 below this, but here it has kind of gone down. So now if you think of, again, you're still talking elastic channel model. So let's say electron is just going elastically. And you use this formula to figure out the current. Now you see you have a problem. You don't know what modes to use because at this end, the number of modes corresponds to this energy. At this end, the number of modes corresponds to that energy. I mean, then physically, you just say that at this end, the electron has a lot more kinetic energy. It's got all this extra energy here, right? So, and anyway, but the point is the number of modes has gone up. So it is almost as if this conductor kind of looks like it got wider. This is because here you got 10 modes, let's say. By the time you come here, you got 100 modes. So it would be almost as if you had widened out the whole thing. And if you widen it out, then you can see that if you just, whereas when you're calculating it this way, it is as if it never widened out. You're missing that whole thing. And so finally, you get a lot more current due to this electric field here. So in that sense, it's not as if electric fields cannot increase the current or cannot have any influence on the current. It is just that in this language, I'll think of it a little differently. But the part I felt can be very misleading overall is always to think of electric field as the driving thing. And because when it comes to small devices, it's very difficult, that gets very confusing. Because as I say, there's electric fields everywhere in a solid. And it is hard to tell which ones are then causing your current and which ones aren't. And, right. But, so for example, if you have two devices, one of which has this, and the other, I'll use a different color chalk, there is no electric field here. It looks like this. So let us say you manage to, you have a really good gate that really holds it there. So it only drops off at the end. So two different devices, same mu1 and mu2. One has an electric field in it, the other has hardly any electric field except right at the ends. So in this case though, when you draw this picture, it would look more like this. And this should have a whole lot less current than that one. And you'd say, well, you'd be tempted to say that, well, it's because of the electric field. Yeah, I guess, yeah, in a way you could say that. That's true. Right?
Are you assuming scattering is occurring? Or not? Is scattering occurring?
Right.
Because this argument requires scattering.
Right. If you had a ballistic transistor, none of this would matter. Because if you had a ballistic channel, that is of course one important point, that if you had a ballistic channel, then the fact that you have 100 modes here makes no difference. Finally, the conductance is limited by the 10 modes. Absolutely. Right. So because in a ballistic case, you don't have this factor. And then indeed the electric field has zero effect on what's going on, really, in this context, right? It really don't do anything in the ballistic context. Unless it can pull this end down. If it can pull this end down, then of course it would give it more modes here. But if it cannot pull this end down, then nothing would happen. That's the understanding. Right. But if you have scattering, then it looks like this. Then as Mark pointed out, in a device like this, it looks as if this L is a whole lot less. Right? There is some effective length that you could use to describe this. So, and but otherwise, I feel that, yeah, and I think anyone who actually is applying this diffusion type of equation, I think they always start from something like sigma d, yeah, I guess what I wrote as chemical potential dz or sigma del mu. That is where people always start from. In the literature, I mean, this is where they would always start from. And then they would say that, well, this chemical potential, you could divide it up into various pieces and then try to extract a drift term and a diffusion term if they want to. Or when you have a heterostructure, you could have a varying mass or things of that sort. And all of that would usually then, you try to figure out what terms you get. But this is the starting point. This is what is really believed. Right? And I'd say more correctly, it is df, or rather del f. I mean, actually there's a function that tells you the occupation of all the states in energy, of different states in energy at a given z. And you should look at the derivative of that. That's really what is important. And this could be replaced with this if you assume that somehow it is close to a Fermi function. And that is sometimes a good approximation, sometimes it's not. That's part about whether you can replace this. And this, let me say a few words about, and that is, so let's go back to our old picture then. So here you have a Fermi function that looks like this. And here you have a Fermi function that looks like this. Now, question is, what is the occupation of the states inside here? Now, if you assume this again, this elastic model, then the way Mark wrote it, he said that, well, you had this density of states, half the states are filled according to this, the other half are filled according to that, actually. Right? And so if you wrote down the occupation of states here, what you'd see is something like this. Because in this region, this is 0, that is 0, so you get 0. In this region, this is 1, that is 0, so you get about half. Roughly, I mean, actually it is like half the states are well occupied, half the states are not. But if you looked at average occupation, it would have looked like that. And then at the other end, it's 1. And this, of course, doesn't quite look like a Fermi function, especially if you put enough voltage on it. And this is actually what the distribution would be if there were no inelastic processes inside your device. If there are inelastic processes, it would tend to try and make this into a Fermi-looking function, because all scattering processes try to restore this kind of function, essentially. Basically, would try to take things from here and put it there. That's what it would try to do. And what often works is, or what often people use at least, even though it's not quite justifiable, is to say that, well, let's assume there's so much inelastic scattering that it makes it look like this. So we assume that there is some local chemical potential, local Fermi function. That's what people assume, again, just to simplify the whole thing. But one interesting point is that if the amount of voltage involved, this mu1 and mu2, if that difference is much less than kT, if it's less than kT, then actually it wouldn't look like this. It would actually automatically look almost like a Fermi function anyway. You can take two Fermi functions which are just a little bit off, less than kT, and add them up. It looks almost like a Fermi function. That's this Taylor series idea. Then even without scattering, it's almost a Fermi function, which means if you, after that you put in some scattering, it won't really do much to it, because it basically is trying to restore a Fermi function. If that's already there, it won't. No, etc. So one last comment maybe, and yeah, are there any other questions about this that you'd like me to answer? So maybe that would be the best.
That step distribution. So you would potentially see that in a device that had that delta U1, U2. Then you would have an IV curve that would look like steps, right?
Oh, this is the occupation. No, but this is not density of states, though. This is the occupation. This is the occupation we are writing, right. No, this is not density of states. This is the occupation. And I would say that in this case, you are better off, you'll get a much better description by not assuming a single chemical potential, but rather two quasi-Fermi levels, essentially. So what I mean by that is, don't think of it this way, but think of it as one thing that is like this, and another thing that is like this, and it's an average of the two. And then call this one mu plus, call that one mu minus, and work with that. That's a much better description of whatever is going on than to try to get one mu into the whole story.
Is this even hold for high voltage? Like it will look like a Fermi function inside the semiconductor?
Not for, okay, a high voltage on a ballistic conductor. That's the part I'm thinking.
Ballistic, one, and second is
yeah, even at, okay, let's just first do the ballistic case. Ballistic case, the thing is that half the states will have this, the other half will have that. So it is so the best way to describe it is two chemical potentials, mu plus and mu minus. Right? And ballistic, that is it. That is it, right?
So even if we far from equilibrium, the inside distribution function will look like Fermi distribution.
Right, because if it is, what I mean is you have one group of states which have this Fermi distribution, and this is the plus group, and then there is the minus group, which has something looking like that. And this is kind of in equilibrium within itself. This is within equilibrium within itself. And ballistic means what we are assuming is there's nothing to take somebody from here to there. And as long as that is true, even with all the inelastic scattering makes no difference, because this is already a Fermi function. What else can inelastic scattering do to it? Now, once you have things that take things from here to there, then of course what will happen is this will tend to come down and this will tend to fill up a little more. Right? And then exactly what it is, that requires,
Stick limit, one carrier is with equilibrium, one contact, another is with
equilibrium. Right. The ballistic limit, it's really that clear, right? And inelastic processes won't make any difference at all.
You can always work with equilibrium coming from
with two quasi-Fermi levels. Right. This is the point I was trying to make, that if you write I equals sigma d mu dz and try to solve this, then you wouldn't quite get the right answer. But if you recognize that there are kind of two equations, and then set one boundary condition for a boundary condition on this on the left and a boundary condition on that on the right, then you would get all the effects, the ballistic part, everything. But that is the important insight.
So the question I had was, why mu does not depend on mu plus and mu minus, does not depend on a channel potential?
Right. So usually the way these work is, so the way I usually think about it is that in these devices in general, you'd have one equation which I've written on top. That is like what you might call a transport equation. Now, where did that come from? Well, what is inside is like the current. That's the sigma d mu dz, as I was saying. And current must be the same everywhere. So di dz is 0. That's kind of like the top equation. Then there is the second equation, which is what I'd call that's the Poisson equation. It kind of looks similar, except that what that epsilon is the dielectric constant, and that's the potential. And that depends on electron densities. Now, in general, all this has to be solved self-consistently. So usually what happens is the following. So supposing you have a conductor here, and you have put some chemical potential mu1, and the equilibrium chemical potential was, let's say, here, and you have put all these extra electrons in, and you're trying, and so you're solving the transport equation, and you're trying to figure out what the electron density is in here. Now, if you do it self-consistently with Poisson, then what will happen is the bottom of the band and all will automatically adjust so that the carrier density, because if you just, so let's say this is the equilibrium mu 0, and you have put some voltage here to raise it, and you pump all these extra electrons in here, that would of course make this very negatively charged. And if it is negatively charged, when you solve it with Poisson equation, this will then automatically go up somewhat, etc. And so all these would be at high bias. You'd have to, this point that we discussed, that saturation current of a transistor can get higher when you put a voltage because of this requirements of space charge, that is how to keep the electron density constant. So the picture I have in mind usually is that there's this two things. One is mu, the other is u. And the u has to do with this, how the band edge moves, etc. And mu tells you how far it is filled. And the difference is proportional to n, electron density, because you have all these states to fill up, actually. So, and what tends to happen is Poisson equation likes to keep this constant, because it really likes to get rid of extra charges in general, anytime. And so, often in any solid, if the mu varies in a certain way, U also tries to vary much in the same way, so as to make this charge density constant. Except that it may not be able to follow it exactly, and so there will be local charges which you have to simulate and calculate. Right? So there could be local charges. Right. But the picture I have also, yeah, this is the mu, that's the U, and the electron density is proportional to that. And the point I tried to make is that current is really determined by the slope of this one, which you can break up into the slope of this and the slope of that. And then one is drift, one is diffusion, etc. But to me, that's a derived secondary step that under certain conditions may be useful. But to me, always the starting point is current is proportional to derivative of the quasi-Fermi level. Yes, please.
Are we using a coarse-grained picture because we are using classical integers to solve for the potentials? So in some sense, we are not looking at atomic scale electric fields. So when does this coarse-grained picture break down? I mean, what is the crossover scale at which this coarse-grained picture will break down and would not be able to use electrodynamics to actually find out the potentials?
Okay.
I'm asking about practical implementation of this. When would this sort of break down? What kind of time not be able to apply?
Yeah, that's the part I'd say, everything we are doing here is what we call this semi-classical transport, right? Semi-classical means there's a density of states which comes from somewhere, which actually could come from some quantum input. That's why it's semi-classical, not fully classical, in the sense the density of states has some quantum input in it. But then after that, it's like cars on a highway. I mean, there's no more quantum physics in this, right? That's the picture here. Now, so that is as far as the transport equation goes. Now, the second equation, that's this Poisson equation. That has to do with this electron-electron interaction, which in general is a very complicated thing. I'd say in solid state, understanding the theory, properties of solid state, that is the one unsolved problem. No one quite knows how to do it accurately, and the Poisson equation is an approximation to that. And there people usually correct for it. I mean, what they know is that the actual potential and electron fields due to other electrons is less than what Poisson gives. Because Poisson is what you usually call the Hartree approximation. And everything else usually will subtract from it. And so people often, when doing this, they will use something less than that. There will be the exchange correlation correction to all this, right? But that has to do with the Poisson equation, the second one. Now, transport part of it, I'd say that, yeah, by doing this, you are missing things like tunneling, for example. That is one reason why you might want to go to the quantum formalism, like tomorrow morning, what I'll talk about. The other thing is usually interference effects. And that is where I guess tomorrow, I'll try to show an example that, when you use a quantum formalism, you actually see interference effects. You get there, but often at room temperature, when you measure it, you never see that. So in that sense, it's almost like the semi-classical one is more correct. Correct in the sense, if correct means, matching experiment, of course, right? That's why. So in that sense, and why is that? Well, that's because in real solids, when you do the quantum picture, usually you're assuming that an electron is going through and see some nice static potential. And then if you have multiple paths, you'll have interference. But at room temperature, it's not a static potential. This whole thing is just jiggling. It's like a very turbulent medium. And so most of these interference effects coming from quantum mechanics are not observed at room temperature. Although these days there are experiments where people have seen a lot of these effects at low temperatures. I mean, in the 1990s, there were lots of experiments like that which show that. So interference effects can be observed. But if your objective is to model a conductor at room temperature, then, there are most cases you are better off using a semi-classical picture. And I'd say that almost the only reason to go to the quantum is if tunneling effects are important. There are all kinds of barriers where, like Mark also showed how for the 4 nanometer MOSFET, there were all these tunneling things that needed to be accounted for, right? Yes.
Is that possible that the phi is too large and the current is too high, so the charge inside the contact does not change fast enough to meet the equilibrium? Is that possible?
So you're saying that if the contact is not connected well enough.
If the current is too large, so the charging side contact respond fast.
That is, I guess, yeah. So in this whole discussion, usually we are assuming that the contacts are always maintained in equilibrium, right? And this is the one point I want to stress is that current flows because, electron goes from here to there, and then all kinds of external forces that we don't talk about kind of relax it and then take it out. This taking it out, and you see, if you never took it out, then you see we wouldn't have a resistor. You'd really have a capacitor. No, because then what would happen is you'd have lots of electrons piling up here. And then after some time, this would float up some, this would come down. What you would have is a capacitor. So when you take a device, so this is the other point I make about electric fields being the driving thing. I mean, you could take this same device and put it inside two capacitor plates. You would have the same electric field. But it would just be a capacitor. I mean, that's it. There will be no current. Current flows because something not in your Hamiltonian, something we don't even talk about, is continually taking electrons out from here and putting them back in there. If that didn't happen, and this is the part where we are kind of including it in our model by saying that contacts are always maintained in local equilibrium, this F1 and F2. So this very complicated process that goes on, how electrons relax and how they get out and all that, we are avoiding that whole thing as a boundary condition, F1 and F2. Now the point you are making, that's true, that in nanoscale devices, one can argue whether your source and drain regions, are they acting as good contacts? In the sense, are they really being able to maintain F1 and F2? Or can they get depleted? And I'd say conceptually quite possible, in which case you should think of them also as part of the device, and the real contact being somewhere else. I mean, where you actually have the solder. I mean, actually have the blob outside. That's the real contact. And the source and drain are also kind of part of the device that can go somewhat out of equilibrium.
So you're effectively saying that the channel is very inelastic, but the contacts, the channel is very elastic, but the contacts are very inelastic. Effectively, you're saying that one has some coherence, the other one is totally non-coherent.
Right. So the channel is small enough that, because this is a small region, and we are saying the limit where everything is quite clear about how to think about it is this elastic resistor, which describes a lot of small devices very well. That is, an electron goes from here to there, and then loses all its energy here. So this energy dissipation, that is because, you see, this is where I say the transport theory is so complicated because it mixes these two things, the dynamics and the thermodynamics. And dynamics part is reversible, in the sense an electron going from here to there is just as likely as an electron going from here to there. You know, if you could picture an electron going from here to there and ran it backwards, it wouldn't look funny at all. It would look exactly quite reasonable. On the other hand, an electron that loses energy and comes out, that's an irreversible process. If you saw the reverse, something from here for no good reason going up there, you'd be pretty surprised. Right, yeah.
How do you delineate the contacts from the channel? I mean, is it so clean? Like one is so well inelastically formed, and one is so coherent.
So the basic difference is just that the contact has many degrees of freedom. So to me, the real thing is that you have this interstate with limited number of lanes, which suddenly broadens out into something with many, many lanes. So that's what really, to me, is the difference between the two. That you have limited channels and then lots of them. Right? So for example, when this question came up earlier, that when you draw these Fs, I drew it like this, and then the question was, but should this be separated or should I join them? Okay? And the argument is what is the argument for joining it? Well, it's sort of like this, that the current is Q over H times M times mu plus minus mu minus. Now, inside I've got only 10 lanes, and so let us say you have a certain difference here that is needed to carry the current. Here, because you have 1 million lanes, you don't need any big difference to carry that same current. But current, of course, is the same everywhere. So the thing about the contact is it can carry all that current without having any significant difference in chemical potentials between the plus and the minus. But I really wanted to stress that the elastic resistor is just a model that we are saying that let's assume this is elastic, and real channels will have inelastic processes in the channel. And under certain conditions, it can change the current. And one of the problems I think I'll talk about maybe on Wednesday, I'll try to show an example where the conductance cannot really be written as F1 minus F2 at all. You know, the basic equation we had there, G F1 minus F2, I'll try to give examples of, even a small conductor where this would give you totally wrong answers. This wouldn't be it at all. So I do not mean to imply that this covers everything, but all I said was it helps you understand a lot of things. Lot of things that are...
We use technologies to describe bipolar junction transistor.
Yeah, that's something I guess we have been working on. But actually the bipolar is a very good example of where you need something a little different. And the reason is something like this. Yeah, actually this example that I give of where ignoring inelastic scattering wouldn't work at all is something like this. Supposing you have a density of states here that is connected to one contact. This is contact 1. And you have a density of states here which is connected to 2, let's say. So one group of states connected this way, one group of states connected that way. Now, if you had an elastic resistor model, only elastic processes go on inside, no current can flow. Because electrons come in here, they can't go anywhere. Now, as soon as you turn in inelastic scattering, of course, there is communication here and current can flow. So this is one example of something that could be quite small, and the elastic resistor model would be just completely wrong. Right? Because you have one channel that is connected to the left, one channel that's connected to the right. Now the PN junction is a lot like that. Because if you draw, those who are familiar with band diagrams, when you draw a PN junction, as you know, this is the picture we usually draw. Okay? This is the p-type P side with its quasi-Fermi level somewhere here. This is the N side. And if you ignore these things, which are not very important here, that's a little bit like what I drew there. That this density of states is filled from this contact, this density of states is filled from that contact, this side, and the current flows because of recombination processes that take you from one to the other. And that's well known that the IV characteristics of a PN junction are strongly influenced by the nature of the recombination processes that go on in the depletion region. So obviously, if you do not include recombination generation processes, you wouldn't get it right. Okay, so. Okay, I think, yeah, thank you for your attention and see you tomorrow.
Here, right? We're assuming we know the density of states at the beginning of the channel. It's that. Is that right? Yeah. Then there are questions. If you get into really small devices, is the effective mass in this very short channel device in that region the same as it is in the bulk silicon? To first order, it's pretty good to remarkably small devices. These days, one of the other reasons that 3.5s aren't quite as attractive an alternative as they were initially is that silicon never stays still, right? These guys are always doing clever things. There's been a lot that's been done in recent years on strain engineering by straining silicon effectively to lighten the effective mass and get a lot of these benefits, which makes it even harder for anything to compete against silicon. But as I said, you work the numbers, it looks like there's an advantage there, but it's got to be done in a well-designed device.
You talk about the contact resistance at 3.5 and your ballistic. So you talk about the ballistic mobility for 3.5. Mm-hmm. It's better than silicon, right?
Yeah, so the ballistic, for a given channel length, I guess this velocity will be higher, right?
But then we've got to get there's an issue of all the extraneous resistance, so of getting that structure, which is a real resistance.
Yeah, all of this parasitic source drain resistance, which, yeah. So some of these practical issues, which are very, very challenging because you're thinning everything down, you're making all of these parasitic resistances higher. These resistances are probably scaling in the wrong direction. They want to go up with scaling because you're shrinking all the dimensions, right? You're shrinking the cross-sectional area of this resistor. Here you're shrinking the channel length, and this is going down.
What's the VT difference, the potential velocity difference?
Pardon me?
What would the velocity difference be between silicon and potentially?
Oh, this velocity here? So in silicon, it's, so one of the things I really should have done, this really depends on where the Fermi level is in the band. When you're a non-degenerate semiconductor, it's independent of the gate bias, and it's 1.2 times 10 to the 7th centimeters per second. When you start pushing the Fermi level up in the band, that velocity gets higher. So under typical on-current conditions, I think this is more like, but we have to think about what the effective mass is in graphene, but similar things happen. If I have frequently I have a high mobility because I have a very light effective mass. That light effective mass is also going to give me a very high thermal velocity. That thermal velocity, remember what the on current was. It was W times Cox times the ballistic injection velocity times Vg minus Vt. So what's giving me the high mobility, part of it is due to low scattering, part of it is due to the light effective mass. The light effective mass is also giving me a high injection velocity. So that's boosting my on current. That's good. I'll have a higher ballistic limit in those materials. Okay. But there's always a gotcha somewhere, right? It's always a trade-off. So there's one more issue that we can't, I probably can't do justice to, but I will point out. In an MOS transistor, so let's say I have a source, and I have a drain, and we have a gate insulator, and we have a metal. Right? When I've been talking about the gate capacitance, I've just written the oxide or insulator capacitance. All right. And that's epsilon of the oxide divided by the thickness of the oxide, which is like a little over 1 nanometer these days. So this is the capacitance in farads per square centimeter. Okay. But that's not quite true because the semiconductor channel itself also has some capacitance. So the actual capacitance is this insulator, or insulator, if you've replaced SiO2 with something else, like Intel has, then it's some other insulator capacitance with a different dielectric constant. But it also has in series with it a semiconductor. Sometimes people call this the quantum capacitance. These two are in series. So here's my gate terminal. Here's the surface of the semiconductor, or the middle of the channel. And the actual gate capacitance is the series combination of two capacitors. The physical capacitor for
NanoHUB.org. You can follow along with this presentation using printed slides from the NanoHUB. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
So we had a question that said, when we talk about high mobility channel materials like 3,5s or graphene replacing silicon, how would it exactly be better? Is it that we can make transistors with the same current levels at longer gate lengths? As using longer gate lengths, it's easier to manufacture and control the channel length. All right, so it's a good question. I can't say a lot about that, and let me. When you make a transistor, the transistor people would like to have a lot of current when the device is on. So at a given voltage, as low as possible, a volt. If you could do a half a volt, it would be even better. You'd like to get a lot of current so that you can charge and discharge all of the capacitances, do the wiring and everything on the chip and run very fast. And you would also like the channel resistance down here to be as small as possible so that the current goes up very rapidly and saturates, and it doesn't take a large drain voltage in order to saturate, because power goes as voltage squared, so you could operate at lower voltages. So you'd like this curve to be steep, and you'd like this value to be high. So down here, traditionally we write the current as W mu. They call it effective mobility. Well, we'll just say mu here. Figure out what mu it is. Gate capacitance, Vg minus Vt times VDS. All right. So this is a lot of the reason that people were really interested in 3,5 transistors or graphene, because the mobilities are very, very high. They looked at this. Maybe this is 200 centimeters squared per volt second for silicon by this insulator, parallel plate capacitor, and the capacitance due to the semiconductor. And this probably won't come up in your lectures later on, but you can show that this semiconductor capacitance under simple conditions is Q squared times the density of states at the Fermi level. Okay. The 2D density of states is effective mass over pi times h bar squared. Right? So in 3,5s, the light effective mass that's giving you the high mobility, that might not be so important because your ballistic mobility is going to limit you, but it's also giving you the high thermal velocity, which is important because it gives you a higher drive current, which you want, is also giving you a lower density of states capacitance here. So if I put these two capacitors in series, it's going to lower the overall gate capacitance. So there's a trade-off. The boost that you get from the light effective mass is offset to some degree by the drop in the gate capacitance. Your charge is going faster, but you have less charge. Now, so the net effect is that you get a benefit. But again, you don't get quite as much benefit as you might have initially anticipated. Right? So people are looking very closely at this. It looks like there might be a win there. It's not quite the slam dunk that you might think of if you had only looked at mobility and you had only looked at ballistic injection velocity. But it looks like if you're careful, there could be a place there where you could design a device and get some improved performance. Okay, anything else I can add to that?
In the ballistic mobility, the thermal velocity Vt, so what's the effective mass we use? Is the effective mass in the metal or effective mass in the channel? Because it's the injected electron from the source, right?
Yeah. So, yeah. Make sure Cyprio agrees with this. What we're doing is electrons are coming in from the source, and we have this top of the barrier. We're populating these states with a Fermi level according to the band structure at the top of the barrier, which we're thinking of as our beginning of the channel. So it's the effective mass at the top of the barrier. Maybe you could get 10,000 on some of these 3 5s. All right, that looks like an enormous boost. All right, but it wouldn't quite work that way. I mean, that would give you more steepness, but you're going to saturate. And also, you can't get steeper than the ballistic limit. So this mobility, really here, 1 over that mobility is 1 over the actual mobility, which might be enormous for these materials, plus 1 over this ballistic mobility. And that's the thing that depends on channel length. So that ballistic mobility, you know, mobility is thermal velocity times mean free path, but in the ballistic limit, the mean free path is the channel length, right? Divided by 2, that's diffusion coefficient, and then the Einstein relation divided by KT over Q. So as you scale and get transistors denser and denser and denser, this ballistic mobility gets smaller and smaller and smaller, and it tends to dominate. So, you know, you get some boost, but you don't get nearly the boost that you would expect just by looking at the differences in the bulk mobilities. Okay. But there is this advantage, you know, alluded to in the second question. You know, is it that we can get the same current levels at longer channel lengths? Yes. So with relaxed geometry, especially if you're looking at RF devices, you can get very high performance. Oops, this should be W over L. I can go to much higher channel lengths where the ballistic mobility is bigger, so it doesn't limit things as much. Now we're limited more by the actual mobility, and that's so much higher in 3 5s or graphene that in a longer channel length device you could still get very good RF performance or high speed performance. So if you're looking for RF performance, that's an advantage. If you're looking for density in a digital circuit, you're going to make these transistors as small as you possibly can. And then this ballistic mobility is going to limit you. Now, also up here, I mean, you tend to get more, more current. You know, you can see that this mobility has a thermal velocity. So 3 5 devices, it's a little bit harder to think about it in graphene.